You ever stop and think how quickly things are changing, especially, in tech? It feels like keeping up requires sifting through just mountains of information.
It really does. Every day, something new.
Yeah, and if you're wondering just how close we are to having, real-world humanoid robots working alongside us, the kind you see in sci-fi, but actually useful, then you're definitely in the right place.
Welcome. Yeah, today we're diving deep into the current landscape of humanoid robotics. We've gone through a whole range of industry reports, latest research papers.
We're having to pull it all together.
Exactly. To distill the key advancements and give you, hopefully, a clear picture of where things actually stand right now.
And it really feels like we're on the verge of something pretty significant, doesn't it? Our sources, they consistently point to this 2024-2025 timeframe as a major turning point.
An inflection point, yeah.
Right. The rapid strides in artificial intelligence are finally meeting some truly impressive hardware developments. Some are even saying 2025 could be as pivotal as, say, the introduction of the iPhone or when ChatGPT went public.
That's a bold claim, but you can see why they'd say it. What makes this moment so distinct, I think?
What is it?
It's this convergence we're seeing. It's not just about building robots that look like humans, but about equipping them with the intelligence, the physical capabilities, to truly operate in human-designed environments.
Right, places built for us.
Exactly.
Yeah.
And perform complex tasks. Think about navigating a warehouse, using tools on a construction site, maybe even assisting in a hospital.
Right.
These are spaces and activities built around, the human form and function.
Okay, and that human-like form, that anthropomorphic design, it isn't just for show, is it? Our analysis shows that it offers a real advantage.
But definitely not just aesthetics. Bipedal movement, walking on two legs, lets them navigate spaces with stairs, uneven ground, things wheeled robots struggle with.
And the hands.
And those human-like hands are essential for manipulating the tools, the objects we use every single day. It's really about seamless integration into our world. And the engine driving all this, the brain, if you will, that lets these robots understand and interact, that's what we call embodied AI.
Embodied AI.
It's the sophisticated software enabling perception, reasoning, physical interaction, all of it working together.
Okay, so let's really dig into this AI piece then. It sounds like this is the core breakthrough that's making these robots go from, interesting lab projects to potentially practical tools. It's like the central nervous system, right? Giving life to the metal.
That's a spot-on analogy. And the recent progress in these large-scale AI models is truly revolutionary for robotics. Our sources really highlight the impact of what are called foundation models.
Foundation models, okay.
Think large language models, LLMs, and vision language models, VLMs. These allow robots to process a huge range of information. They can understand natural language commands, sure, but also interpret complex visual scenes from cameras, sensors, multiple inputs.
So it's way beyond just simple pre-programmed actions then.
Oh, absolutely. They can understand context, react to more complex instructions, visual information.
Yeah.
Not just follow a rigid script.
That feels like a game changer.
It is. And the development of robotics-specific foundation models takes this even further. For instance, you've got NVIDIA's project GR00T. That's GR00T.
GR0002.
Stands for Generalist Robot 00 Technology. And there's also work from Physical Intelligence with their model PIO. What's really noteworthy about GR0T, for example, is how it's trained. Massive data set, real-world data, synthetic data, even video demonstrations from humans.
So it learns from all sorts of examples.
Exactly. The goal is to imbue robots with generalized reasoning and manipulation skills that can be applied across different robot designs, different environments. It's a real leap towards, adaptable intelligence.
So the big trend is towards these generalist robots, not just stuck doing one single narrow task. That sounds like the key to making them actually useful everywhere.
Absolutely. That's the dream, really. And to get that versatility, different learning methods are crucial. One key approach is reinforcement learning, or RL.
RL, okay. Heard a lot about that.
In essence, robots learn through trial and error. Often this happens in simulated environments first. They get rewards, digital rewards, for doing things right.
Like learning to walk by virtually stumbling until they figure out the right balance and coordination, that kind of thing.
That's the core principle, yeah. It helps them develop really robust strategies for movement, for picking things up, without explicitly programming every tiny step.
Okay, what else?
Then we have imitation learning, or IL. Here, robots learn by observing humans performing tasks.
Watching and learning.
Pretty much. This could involve a human directly controlling the robot remotely, that's teleoperation, or even wearing a motion capture suit, like in the movies, to record their movements. Tesla, for example, is using VR motion capture to train Optimus.
Wow. So they put on a VR headset and show the robot how to do stuff.
Exactly. Showed exactly how to perform actions. Allows for a more, maybe intuitive transfer of skills.
That's incredible. But hang on, there must be a challenge in taking something learned in a nice, clean simulation or from a direct demo and making it work in the messy, unpredictable real world.
You've nailed a major hurdle. It's known as the sim-to-real gap.
Yeah.
Getting a robot that performs perfectly in simulation to work effectively in a cluttered factory or on a dynamic construction site.
Yeah, reality is messy.
It is. So researchers use techniques like domain randomization. This basically means making the simulation less perfect on purpose.
Oh, interesting. How?
Introduce variations in lighting, textures, object positions, even the physics engine itself. The idea is the robot learns to be more adaptable, more robust to real-world imperfections. It's about training them to handle the unexpected.
Okay, like training a pilot in a simulator that throws in unexpected wind shear or engine trouble, so they're ready for it.
Precisely. A very good analogy.
Yeah.
And all this learning, all this perception, it needs a framework for action, right? Which brings us to control architectures, how the robot's brain actually tells its body what to do.
The control system.
Yeah. Traditionally, we've seen model-based control, using mathematical models of the robot and its environment to predict and control movements. Things like model predictive control, MPC, or whole body control, WBC.
And these are good for?
They excel at ensuring stability and really precise motion, making sure the robot doesn't just, fall over or make jerky, unpredictable movements.
The established, reliable way.
Kind of, yeah. But the big trend now is towards integrating these model-based approaches with the learning-based ones we just talked about, the RL and IL.
Getting the best of both worlds.
That's the goal. Leverage the reliability and predictability of models with the adaptability and generalization you get from learning. We're also seeing more hierarchical control structures.
Meaning?
High-level AI policies set the overall goals, like pick up that box, and then lower-level controllers handle the detailed motor commands, the joint movements. And something really cutting edge is the emergence of fully differentiable control architectures.
Differentiable. Sounds complex.
It is, but the idea is to seamlessly blend the physics models and the learned data right into the control process itself, creating a more unified, adaptable system.
Wow. It sounds like a really intricate dance between different control strategies. Okay, let's shift focus a bit. Let's talk about the physical form of the hardware, because all that fancy AI needs a capable body, right, to interact with the world.
Absolutely critical.
Yeah.
And our sources show some really significant advancements happening on the hardware front as well.
Where do we start? Actuation?
Let's start there. Actuation, the mechanisms that actually move the joints. A major shift is underway. We're moving away from hydraulic systems.
Like the old Boston Dynamics Atlas, the really noisy one.
Exactly like that one. Powerful, but complex, potentially messy. The trend is strongly towards electric actuators now. You see this in the new Electric Atlas, Figure 02, Tesla's Optimus, Apptronik's Apollo, Unitree's robots. Pretty much across the board.
Why the big switch? I always thought hydraulics meant serious power.
They do offer high power density, true. But electric actuators bring a lot of advantages for these newer humanoid designs. They give you much greater precision, finer control over movements.
Smoother motions.
Smoother, yeah. And they're generally more energy efficient. They operate much more quietly, which is a big deal if they're working around people.
Good point.
Plus, they tend to be easier to integrate with all the complex digital control systems we just discussed. We're seeing specialized electric motors too, like quasi-direct drive, QDD motors for better torque.
And sensors built right in?
Yeah, some actuators are integrating sensors directly proprioceptive actuators. They give really detailed feedback on position, speed, force, right from the joint itself.
So electric seems like the future for most joints.
It's the dominant trend. But it's important to note, some companies, like Sanctuary AI, they're still using hydraulics, specifically in their Phoenix hand.
Ah, okay. Why just the hand?
Because for really complex, fast, powerful hand movements, that hydraulic power density and rapid response might still be the best option right now. So it's often about choosing the right tech for the right job within the robot. A hybrid approach sometimes.
That makes total sense. Use the best tool for the task.
Okay, what about sensing? How do these robots actually perceive their surroundings? That awareness has got to be crucial.
Absolutely fundamental. They're typically loaded with a diverse suite of sensors. Vision, of course, is key. RGB cameras for color, depth sensors to understand 3D space.
Like the Kinect sensor, sort of?
Similar principle, yeah. LiDAR light detection and ranging is also common for creating detailed 3D maps of the environment.
What else?
IMUs, inertial measurement units, help with balance and orientation, knowing which way is up. Force and torque sensors let the robot feel interactions, how hard it's pushing, how much weight it's holding.
Feeling the forces. But a really rapidly advancing area, and super important, is tactile sensing, giving robots a sense of touch.
Electronic fingertips?
Kind of, yeah. This is crucial for anything requiring delicate manipulation, secure grasping, knowing if something's slipping.
How do they do that?
Various technologies. Piezoresistive sensors change resistance with pressure. Capacitive sensors detect changes in electrical fields. There are even vision-based tactile sensors, tiny cameras looking at how a soft surface deforms.
Wow.
And magnetic ones like Wriskin, Sanctuary AI's Phoenix Hand, back them, uses arrays of microbarometers for really fine-grained touch feedback.
Microbarometers, like weather sensors.
Essentially, yeah, but tiny and sensitive to small pressure changes. Ultimately, though, just like us, it's the fusion of data from all these different sensors that lets the robot build a rich understanding of its environment and how it's interacting.
Seeing, feeling, balancing. Okay, got it. What about keeping them powered up? The batteries must be a huge bottleneck, right? How long can these things actually run?
It's definitely both a key enabler and a significant challenge.
Huh.
Currently, most use lithium-ion or lithium iron phosphate LiFePO batteries, common chemistries.
And the runtime?
That varies. Optimus is reported around 2.3 kilowatt hours. Unitree's H1 is smaller, under 1 kilowatt hours. But the big challenge is runtime. You often hear figures like 2 to 5 hours on a single charge.
That's not a full workday.
Not even close for many applications. So there's a massive need for batteries with higher energy density, more power, less weight and size. And they also need high power output for those dynamic movements, bursts of energy.
So better batteries are critical.
Critical, along with efficient charging, maybe even quick battery swapping. Engine AI is looking into swappable systems for their SE01. And of course, safety is paramount. Smart battery management systems, BMS, are crucial.
And longer term.
Eyes are on next-gen chemistries, like solid-state batteries. They promise better energy density and potentially improved safety. But that's still a bit further out for widespread use.
Okay, so power is a work in progress. Makes sense. And holding all this tech together, the materials and the actual physical design must be pretty important too, right? For agility, efficiency.
Absolutely. You need them to be strong, but also lightweight. So lots of lightweight metals like aluminum alloys, titanium, and increasingly advanced composite materials. Minimize weight to maximize agility and save energy.
How are they building them?
Advanced manufacturing techniques are key. 3D printing, for instance, is used in the new electric Atlas. It allows for complex, optimized part shapes that might be hard to make traditionally.
And repairs, upgrades.
That's where modular design comes in. We're seeing a growing trend towards building robots in modules. Makes maintenance easier. You can swap out a damaged arm or leg, maybe upgrade the sensors or hands later without redesigning the whole thing.
Smart, more flexible, future-proof, like building with Legos almost.
A very sophisticated set of Legos, maybe. But yeah, that's the idea. It helps manage development and upkeep.
Okay, so we've got the AI brain, the improving hardware body. Let's talk about movement again, bipedal locomotion, just walking on two legs. You said it's hard, but how far have they actually come?
It is incredibly hard. Just think about the balance and coordination we use without thinking. But the progress is significant. We've moved way beyond that slow, cautious, quasi-static walking you might have seen years ago.
You mean like move one foot, stop, check balance, move the other.
Exactly. Now we're seeing truly dynamic gaits. Remember those Boston Dynamics videos? Atlas running, jumping, doing parkour, even backflip.
Yeah, those were mind-blowing, hard to forget.
That showcased a massive leap in dynamic capabilities. Now, achieving that requires really advanced control techniques.
We touched on those.
Right. The model-based methods, LIPM, MPC, ZMP, whole body control, they're still fundamental for stability, basic movement planning. But as we said, learning-based approaches, especially RL, are really pushing the boundaries.
RL helps with the tricky stuff.
Yeah, RL has shown amazing success in getting robots to handle really challenging, uneven terrain, dynamic obstacles, even those parkour moves. It learns robust strategies through simulated experience.
And what about doing things while walking?
Yes. Loco manipulation. That's a critical area right now. Being able to use the arms, perform complex tasks while maintaining stable balance on two legs. That's really hard.
Like carrying a tray of drinks across a bumpy lawn?
Exactly. Or using a tool while walking on a scaffold. And crucially, researchers are working hard on recovery behaviors. How does the robot react if it gets pushed? Can it recover from a stumble? Can it get up after a fall?
Fall recovery is important.
Very. And to track progress objectively, people are developing standardized benchmarking platforms, ways to actually measure and compare how well different robots walk, run, and handle disturbances.
So it's not just about flat floors anymore. It's dynamic movement, doing tasks, handling bumps. Much more like us. Okay, speaking of doing tasks, the hands, that seems like the other massive challenge. Replicating human hand dexterity.
Wow, you're absolutely right. The human hand is just an engineering marvel of biology. Think about it. 27 degrees of freedom ways it can move independently. Plus, that incredibly dense network of touch sensors giving constant feedback.
Yeah, our hands are amazing.
Replicating that in a robot hand, that's a major, major technological frontier. But we are seeing real progress.
Oh, so?
Well, robotic hands are getting more degrees of freedom, allowing more complex movements. Sanctuary AI's Phoenix hand boasts 20, maybe 21 DOF. Tesla's Optimus Gen 2 has 11, but they're reportedly aiming for 22 in Gen 3. Figure O2 has 16.
Still fewer than a human, but getting closer. A lot of moving parts.
A lot. And actuated different ways, electric motors, tiny tendons, even hydraulics like in the Phoenix hand. And as you said earlier, that tactile sensing is just absolutely essential for the hands.
Can't really manipulate things without feeling them properly.
Exactly. You need touch to grasp securely without crushing things, to detect slip, to handle delicate objects. So integrating advanced tactile sensors is critical for getting towards fine manipulation.
But even with a great hand, teaching its skills must be hard.
Oh, incredibly challenging. The sheer number of ways the joints can move, the high dimensionality, makes manual programming almost impossible for complex tasks. The physics of contact, how fingers interact with objects is super complex.
And the sim-to-real gap again?
Still a big issue for dexterity, maybe even more so than for walking. Plus, getting enough good training data for complex hand skills is tough.
So how do they teach them?
Again, it comes back to reinforcement learning and imitation learning. Often used together, heavily reliant on simulation to generate enough experience. Trying to teach the robot those intricate grasps and manipulations.
And benchmarks for hands, too.
Yep. Just like locomotion, there's a growing need for standardized benchmarks to measure dexterity. Things like Humanoid Bench or the Elliott and Connolly benchmark are emerging. The overall focus is definitely shifting. It's not just about walking or manipulating, but integrating both. Loco manipulation, using skillful hands while moving effectively, that's key for practical work.
It really sounds like we're right on the cusp then, seeing these truly capable humanoids move out of the lab into the real world. And our sources give us a great snapshot of the leading platforms driving this, right?
Yeah, it's a fascinating landscape right now.
Yeah.
Let's maybe tick through some of the key players. Boston Dynamics, obviously everyone knows Atlas, but they've pivoted.
Right, the new electric Atlas.
Exactly. The old hydraulic one is retired. This new one is explicitly designed for commercial applications. They've announced work with Hyundai's Robotics and AI Institute, using RL for real-world tasks, and crucially, they're testing it in automotive manufacturing.
So less backflips, more factory work.
Seems to be the direction, a clear move towards practical industrial use.
Okay. Then there's Tesla Optimus. Huge public interest there.
Definitely high profile. Musk's vision of mass-producing affordable humanoids is ambitious. They've shown Gen 2 prototypes, walking, sorting things, balancing.
And Gen 3.
Planned to be faster, more dexterous, maybe even voice interaction. They're leveraging Tesla's AI from self-driving, plus their manufacturing muscle. The big headline grabbers are the production goals, and that target price, $20K to $30K range.
If they hit that price, wow.
Huge if. Those timelines and prices are definitely still debated within the robotics community, but the ambition is clear.
Okay. What about agility robotics? Their digit seems further along in actual deployment.
That's right. Agility has a strong focus on logistics, warehouses. They have a big deal with GXO Logistics, putting Digit to work in real warehouses. They've also got the Agility Arc platform.
What's that?
It integrates Digit with other autonomous mobile robots, AMRs, for broader material handling. It's basically the first commercial system for managing a fleet of humanoid robots. And they're scaling up production at their RoboFab, aiming for thousands per year.
And they offer it as a service.
Both robotics as a service, RAS says, pay for usage and direct purchase. So definitely pushing for practical, scalable solutions now.
So Digit is actually out there working. Figure AI, they seem to pop up really fast and land big partnerships.
Incredibly rapid development there. Their Figure 02 robot is aimed squarely at industry, and that partnership with BMW is huge.
What are they doing at BMW?
Testing them for handling sheet metal at the Spartanburg plant. Early reports mention big improvements in speed, accuracy, handling thousands of operations a day. They're also working with OpenAI on AI, NVIDIA on simulation.
Covering all the bases.
Seems like it. They're building their own factory, BoQ, and expect Figure 03 next year in 2025. That BMW deal is a major validation for tough industrial jobs.
Definitely sounds like it. Okay, Sanctuary AI and Phoenix, their focus seems different, more on general intelligence.
Yeah, Sanctuary's core is their Carbon AI system. The goal is truly general-purpose robots for a wide range of tasks. The Phoenix robot, with those very dexterous hydraulic hands and advanced touch sensing, is the body for that brain.
Have they tested it widely?
They say they've tested on over 400 tasks across 15 industries, really aiming for broad applicability. The first deployment is with Canadian Tire, exploring a labor-as-a-service model.
So providing robot labor, not just selling robots. Interesting.
Yeah, less about specializing in one industry, more about a capable brain and body adaptable to many roles.
Okay, Avtronic Apollo. They got a lot of funding recently.
Yeah, Apollo's designed with human-robot collaboration and mind safety is a big emphasis. That funding shows confidence. Partnerships with Google DeepMind, NVIDIA. Key features are hot swappable batteries, modular design.
Where are they targeting?
Logistics, manufacturing, retail. They have pilots running with Mercedes-Benz, GXO, Jabil. So focused on getting into real industrial settings, working alongside people.
Safety and collaboration as key selling points. Makes sense. Now, Unitree from China. More affordable options.
Definitely disruptive on price. The H1 model set a speed record for walking. The G1 is smaller, even cheaper, like $1610K base price. They have mass production plans, aligning with China's robotic strategy.
And they're positioning the G1 differently.
Yeah, kind of as an AI-powered avatar. Very flexible, expressive movements. Suggest maybe broader applications beyond just factory work eventually.
That low price could really shake things up. Okay, finally, 1X Neo. Backed by OpenAI, but aiming for the home.
Yes, 1X has a very distinct focus. Domestic consumer market. Their NEO robot uses tendon-driven joints, which they say are safer for around humans at home.
How does it learn?
RL, again, based on human motion capture data. They've also developed their own in-house LLM for natural conversation. They're doing home pilot tests now.
And their goals?
Very ambitious. Millions of units by 2028, price comparable to a car. Totally different segment than most others who are focused on industry first.
It's just fascinating seeing all these different strategies and target markets emerging. And like our sources show, there are plenty of other players too. Nira, NGI, UTech, all over the world.
Yeah, US, China, Europe. It's a global race.
That comparative overview table we looked at really helps visualize it. The design variations, the dominance of electric actuation now, but also how central AI and sensing are to all of them.
Yeah, that table is useful.
And what's really striking is, despite the diversity in design and targets, those underlying technologies we talked about, the AI advancements, electric actuators, sophisticated sensors, they're becoming the common foundation.
All building blocks.
Exactly. And those strategic partnerships, AI companies, hardware makers, industry specialists, they seem absolutely crucial for speeding up progress and getting these things deployed.
So, wrapping this all up.
Yeah.
It really feels like humanoid robotics is at a genuine turning point, a pivotal moment. We're seeing huge tech breakthroughs.
Definitely.
And a real push towards practical applications, especially in industry and logistics. It's gaining serious momentum.
That's absolutely right. That convergence of smarter AI and more capable hardware is clearly the engine driving it all. But, it's also crucial to remember there are still big technical hurdles to overcome. Still challenges.
Big ones. And we absolutely need to think carefully about the safety, the ethical implications as these machines become more integrated into our world.
Absolutely. Which leads to a final thought for you, the listener. As these increasingly human-like machines become more capable, more integrated, what new skills might you need to thrive in this evolving landscape?
That's a really good question to ponder. There's so much more to explore here.
Definitely something to think about. We encourage you to dig deeper into the resources. Thanks for joining us for this deep dive into humanoid robotics.
Yeah, thanks for tuning in. We'll catch you next time.